Yesterday, we talked about how water is actually less dense when it's frozen. And we said that had to do with the polarity of water, and that the positive ends of a water molecule, so the hydrogens, are attracted to the oxygen ends or the negative oxygen ends. So instead of just water molecules coming close together when it forms a solid, so when it turns into ice, and just kind of being really close together like it would be for other liquids, so kind of like this image on the left, those attractive forces of water molecules actually cause them to form these hexagon shapes with a lot of space in between each of those molecules. Okay, that will cause the water molecules to actually expand, and that's why ice is less dense and actually floats. Okay, we also mentioned here that actually when the ice melts from this iceberg here, it's going to turn into water, but it's actually going to be really cold water, which is more dense. Okay, so cold water is more dense than hot water. So if the iceberg were to melt, it would go from floating in the form of ice to actually sinking down to the bottom of this body of water. And that's because cold water is more dense than hot or warm water. Why does density even matter? Well, density of water, that property of water, is actually really important to the environment. So it says here, it prevents water from freezing from the bottom up. Ice forms on the surface first. The freezing of the water releases heat to the water below, creating insulation. And it makes transition between seasons less abrupt. So what's really cool about ice actually being least dense and floating on the top of our bodies of water is that it helps protect all the organisms that live in those bodies of water. So the organisms that live in marine environments. Okay, if ice is forming at the top, then we don't have to worry about the entire pond, let's say, any type of body of water from freezing entirely. If it were to freeze entirely, then all of the organisms that live inside that body of water would freeze as well. But because when water gets really, really cold and turns into ice, remember, it actually expands, becomes less dense, and floats to the top. It actually acts as an insulator. Okay, so that means that it keeps the rest of the water from freezing. Okay, it helps trap in some heat. Now, another property of water that's really cool is what's called specific heat. Okay, specific heat is the amount of heat that must be absorbed or lost for 1 gram of a substance to change its temperature by 1 degrees Celsius. Okay, so that is what specific heat means. Now, what's cool about water is that it has a high specific heat. So it actually needs a lot of energy to heat up by 1 degree. That also means it releases a lot of energy when it cools down by 1 degree. This is really important for our marine environments because oceans actually help stabilize Earth's temperatures. Okay, because of that high specific heat of water, it helps the Earth from getting too hot or too cold. It makes sure that marine environments have more stable temperatures, and that coastal areas have mild climates. A good example to use, one that you guys have probably maybe experienced, is if you've ever been to a beach, you've stepped on the sand, you know how hot that sand can get. But when you step into the water, it's pretty cool. We could also look at a pool. So maybe a pool in your backyard or the community pool. The ground outside of the pool is going to be hotter than the water that's actually in the pool. Now, both the water, like both the ocean and the pool, are getting the same amount of sunlight beating on them as the ground around it, or the sand around it. But those bodies of water, they're a cooler temperature. And that's because it takes more energy to actually heat up water. So instead of that body of water getting so hot from the sun that it maybe boils and kills all the organisms, it can take a lot more energy. It's going to take more energy from the sun in order to heat up. This is good to keep in mind when it comes to climate change as well. Okay, because our water, our oceans, they do as much as they can with absorbing as much heat. But as temperatures continue to rise, our oceans are going to continue to rise in temp as well. Okay, the next property is the fact that water changes Earth's surfaces. Okay, and we're going to talk about 2 processes in which that happens. And the first one is weathering, so breaking down rocks or minerals. And the next one is erosion, so removing Earth's materials through weathering and moving. And here's a side-by-side. So weathering causes rocks to break down, while erosion actually moves the sediments to another place. Okay, so weathering causes rocks to break down, whereas erosion then moves those sediments. So here we have a question: why does water form these ice crystals when it freezes in the ground? So I want you guys to actually pause and try to answer that question for me. It tells you there's ice crystals, and it's what we would call frost wedging in the soil. Why does water form these ice crystals when it freezes in the ground? Okay, so we said that water, if it freezes, it turns into ice. Okay, when it turns into ice, it actually expands. Instead of freezing and mixing in with the soil, like mixing in with that soil that we see here, those particles are going to expand, so they're going to form their own little crystals that you can see. Okay, there is no mixing of that water within all of the soil particles and just kind of hiding. Instead, those water particles are very attracted to each other, and when they freeze, they're actually going to stick together and then expand into what we know as ice. Okay, this has a big part to do in weathering. Okay, we can add that onto here to this idea of thermal expansion and contraction. So whenever rocks or soils go through that repeated heating and cooling, it's going to cause those substances to actually crack and separate. So in like our example over here with frost wedging, as the soil, like as all the water particles in the soil actually freeze, they're going to cause that causes the water particles to expand. And after a period of doing that, of expanding as it freezes, and then actually melting and contracting, that can cause all of the particles around it to actually break up or to weather. So how do you think this kind of weathering happened? Looking at this image here. Pause for me and try to answer that. We see this really cool rock that is inside of a body of water. And we can see that some of the rock has actually broken down. How do you think this kind of weathering happened? Okay, so a difference in the tides, right? As that water is moving in and out of this ocean front here, as it continues to hit this rock, it can cause that breakaway of that material. Okay, this is close to the coast. We could also see some freezing here that could cause some of that contraction and expansion that we talked about, that would cause the rock to further break apart. Okay, so we could have some physical weathering here. We could even have that thermal weathering as well. Okay, a third type of weathering would be chemical weathering. So keep in mind that water can carry other chemicals and dissolved materials from rocks. Those minerals can move to the oceans or deposit, like this stalactite. Sorry, stalactite. But with chemical weathering, we have those chemicals that are being carried in water actually reaching the soil or rocks and causing some reactions to happen that would cause the rocks to actually dissolve or break up. Remember, weathering is important. Okay, when the tiny fragments in rocks mix with organic matter or material, you get soil. Okay, so weathering helps produce soil and is really important. Lastly, we have erosion. Remember, weathering is breaking down of those materials. Erosion is actually moving Earth's materials. And that can happen through these processes of water, wind, and gravity. And I apologize, guys, I'm running out of time. But erosion, tides move coast